Okay, sorry for the interruption. So I hope everyone is back. We'll proceed now. So we have done a derivation for the rise time, and now it is peak time. The definition is it is the time required to reach first peak or maximum peak that we have seen in the time response graph. So this is called as first peak, also as maximum peak. So you can ask me a question that why there is no maximum peak in the subsequent oscillations. So keep this question in mind. You will get the answer for that uh, once we start with the stability analysis of the systems. Fine. So this, please remember this uh, diagram, and the next, what is the expression for this? What is the expression for peak time? So we can derive the expression for peak time using maxima minima concept. So that is very simple. So we'll straight away start doing that. So we already have derived the expression for output of a second order system as C of t equal to, okay, this expression, and phi is given by this expression. I hope everyone can remember this. Fine. Omega d is omega n square root of 1 minus zeta square, damped frequency of damped oscillations. Okay. So from the tan phi or phi equal to expression, we can also write a triangle like this. So tan inverse of square root of 1 minus zeta square divided by zeta goes like this. This is basic trigonometry, nothing to explain much. And let us call this as equation 1. So maximum peak, we know Tp is with respect to maximum peak. We'll use this concept for the derivation. So how we can make use of maxima and minima? So Tp can be obtained by differentiating the first equation, that is the output equation with respect to t, and equating it to 0. So this is equation 1. So we have to derive this with respect to time and equate it to 0. So that's how maxima minima goes. Maxima minima derivation goes. So since we are interested in time, we are differentiating with respect to time. So dct of dt equal to 0 we have to make. So let us start the differentiation. So first unity 1, which is constant. So differentiation of a constant is 0 because it doesn't vary with respect to time. So that's how it goes. 0 minus. So now we have two terms. E raised to minus zeta omega nt and sin omega dt. Two terms associated with the time. So I'll keep the first one as it is and differentiate the second one. So sin will become cos omega dt and into omega d. Simplest of the simplest. Next I'll keep the second as it is and differentiate the first one. So exponential term as it is, e raised to minus zeta omega nt is e raised to minus zeta omega nt and minus zeta omega n. So minus and minus both sides. Sorry. So this minus into minus will become plus. Not much difference. So all are multiplied. Okay. So eliminate the common terms in the equation. Anyhow, we are equating to 0. So e raised to minus omega n is common both sides. Then omega d has a omega n here. This omega n and this omega n will cancel. Okay. Then this denominator is common. Fine. So we have cancelled all the common terms. So what is remaining? So this 1 minus zeta square is remaining. Square root of 1 minus zeta square. And then keep cos as it is. Then plus zeta is remaining here. Zeta sin omega dt plus phi equal to 0. Okay. So now I have replaced t with tp. Okay, we have to replace t with tp because maxima or minima occurs only with this condition. Okay. So that's it. Now we need to simplify this expression to find TP. So how to proceed? So now we used one triangle concept in that you can denote sin phi and cos phi directly. So sin phi is Square root of 1 minus eta square. Okay. Square root of 1 minus eta square by 1 is as good as square root of 1 minus eta square. And cos phi is just zeta. Okay. Just zeta. So not a complicated replacement. So wherever you have square root of 1 minus eta square, make it sin phi. Remaining thing as it is. And we have zeta here, it is cos phi. Remaining thing as it is equal to 0. Equal to 0. So let me write this as sin A cos B minus cos A sin B for, okay, not visible, just a second. Yes, now it's clear. So I'll write it in the form of sin A cos B and cos A sin B, so negative sign. It is as good as sin A cos B minus cos A sin B equal to 0 with A as omega d Tp plus phi and B as phi, just phi. So I have made a small mistake here. T should be Tp. All T should be Tp here. So this is the simplification of sin A minus B. This is a simplification of sin A minus B. So what is sin A minus B will be sin omega Tp plus phi minus phi equal to 0, or sin omega dTp equal to sin inverse of 0, which we had already done, equals to n phi. So now write omega d as square root of 1 minus eta square into omega n into Tp equal to n pi, or Tp equal to n pi by omega n square root of 1 minus eta square seconds. Okay, so this is expression for Tp, but here is one small question. What should be n? What value of that n will take up? So let me answer this question. N can take any values, 1, 2, 3. Oh, sorry. Yes, n can take any value as 1, 2, 3, 4. But since for the peak time, the definition says that it is time taken to reach the first peak, our n should be 1. Okay, our n should be 1. Please remember this point. N is 1 here, and whenever it is asked to find peak time, you should always replace n by 1 and calculate. So I have made a generalized derivation for peak time. Therefore, for first peak, it is n equal to 1. For second peak, it is n equal to 2. For third peak, it is n equal to 3. It goes on like that. Okay, and whenever it is asked to find peak time, it is by default first peak only. Please don't get confused. So I hope I am clear. Not much big derivation. Next, we will have the third time domain specification, which is maximum overshoot, or EMP. Please look at the representation of MP carefully. MP is not from 0 to peak value. Percentage of peak overshoot is not from 0 to peak value, but it is from final value C of infinity to the peak value. So this is again a third important time domain specification. Let us look at the definition. So before definition, 3 terms you should understand. Okay, sorry. So these 3 terms are very important. First is C of Tp. So C of Tp represents output at peak time. Output at peak time or maximum peak value. So we have x-axis with time and y-axis with magnitude. So C of Tp means it's obviously the maximum peak. What is second term? C of infinity. It is final value. So this pink colored mark, which I have written as 1 or C of infinity, is called as final value of the output, or it is unity for the step input. The ideal case. In most of the practical cases, C of infinity may change, but since we are doing with the unity step input, C of infinity means it is final value. Third one is, though we write maximum overshoot as MP, it is represented as percentage MP or percentage of peak overshoot. Okay. So these three terminologies just recall while doing the derivation. So now look at this diagram and let me write what is MP. Just this much of magnitude. Okay. So how I can write this MP? It's very simple. It is this value minus this value, final value. So I just need the magnitude of overshoot. Okay. How much shooting is happening. So when I need magnitude, it is difference between this value and the final value. So how one can write this MP as C of TP minus C of infinity. C of infinity. And if I want percentage of MP, then there is a small change in the representation. So what I should write is by what percentage of final value the overshoot is occurring. So this makes sense. Okay, then I write percentage of MP by what percentage of the final value the overshoot has occurred. So what is meant by this? Let us see. It is C of Tp minus C of infinity divided by C of infinity into 100 into 100. So how we can say about percentage MP, what we can say about percentage of MP. So look at this simple graph. Imagine we have the peak value is 1.2 and input is 1. So what is my MP? MP is this minus this value. So this is what MP is. And I can write straight away as 1.2 minus 1 equal to 0.2. This is only MP, peak, maximum peak. If I want percentage of maximum peak or percentage MP, it means it is by how much percent of the final value it is shooting, overshooting. So what I will do, C of Tp minus C of infinity, which is unity, divided by C of infinity, which is again unity, into 100. When you do this, you will get 20%. So what you can say, 20% is the peak overshoot, or the overshoot is occurring with 20% of its final value. Okay, 20% of its final value. I hope it is clear for everyone. So this is one of the formula expression for percentage MP. So there is another expression in terms of zeta and omega n, you can say. So let us derive that expression for MP. So let C of infinity be 1 because we are doing for a unity step input. And we know that MP is C of Tp minus C of infinity. So therefore it is C of Tp minus 1 because we know C of infinity. And C of Tp, what is C of Tp? C of Tp nobody can calculate with a without a value. So we don't know what it is, what actual value it is, but we know the value of C of infinity. So let us proceed how we can derive. So now what I will do is I will rewrite the C of Tp as it is with the T replaced by Tp. So C of T we knew. Now I am just substituting it here with a change in Tp and minus of 1 as it is. Minus of 1 as it is. So what we also know? We also know Tp is equal to n pi by omega n square root of 1 minus zeta square, which we did previously, and n equal to 1 for first peak. Therefore this is pi divided by omega n square root of 1 minus zeta square. So what we do now, we straight away substitute it here in this expression. Okay. So some may be asking why all these substitution, simplification. Let it be as it is. We'll directly substitute there only. Why to do make simplification and all? So like these are these derivations, of course. Your question is valid. When software can do everything, why to derive? But as a engineer, one should be a good technical writer also. So one way the simplification helps us to interpret the things easily to other readers. So everyone should make a habit that whatever you understand, sometime or someday you should put it in a technical writing, and your technical writing should be readable by everyone, every scientist, every engineer. So that's the reason this some derivations are very important to practice or to understand to what extent we can simplify, to what extent we can make the thing simple for a reader. So that is the main intention. Okay. And other intention may be to increase the syllabus content. That is secondary. But primary intention is one should know how to write the complicated mathematical things into a simple thing for a reader. So this, of course, we are about to simplify. So 1 and minus 1 will cancel, and I will substitute TP. I'll substitute TP, okay, at an exponential, okay, at this TP here, then it is zeta omega n as it is, and peak time expression is this one. So pi divided by omega n into square root of 1 minus zeta square, or square root of 1 minus zeta square into omega n, both are same. So omega n and omega n will cancel, the denominator is as it is. Then sine omega dtp plus phi, here also I am making a substitution. Phi divided by 1 minus, okay, zeta square into omega n, this and this will cancel. So what we have, sorry, sorry for this. So we have, observe carefully, only zeta minus zeta into pi divided by square root of 1 minus zeta square and whole divided by square root of 1 minus zeta square into sine pi plus phi, which is minus sine phi. Okay. So how we get that answer. So into minus sine phi, and one can easily simplify to the next level. Minus and minus we get plus. So this is MP, and there is one last step again to replace sine phi from the triangle. So we already knew sine phi expression from triangle. If you substitute, we will get 1 minus theta square, 1 minus theta square will cancel out. So MP is equal to e raised to minus theta pi, 1 minus theta square, and okay, I have written the step again. So finally percentage MP is e raised to minus theta pi divided by square root of 1 minus theta square into 100. Okay, so this is as good as writing in terms of zeta. So both expressions are true for the percentage peak overshoot. Next we start with the fourth one, settling time. So the settling time definition is very specific. It is time required by the response or transients to reach and stay within plus or minus 2% of the steady state value or final value. So now I'm introducing one more terminology, steady state value, which also means final value. So steady state value in the sense where there is no more oscillations. So this definition is quite different. It's time required by the response or transients. So another terminology, transients, which in simple term means oscillations. So oscillations should reach and stay within plus or minus 2% of the final value. So let us look at the graph. So in the graph, I had marked 0.98 and 1.02. So which represents, these green color lines represent plus or minus 2% of the final value. Plus or minus 2% of the unity step input. Unity. Okay. So one can clearly see that when our oscillations have reached and stayed within plus or minus 2%, I have marked that particular point as TS. Okay, as TS. So I said earlier that some correction with the definition of transient. Oh, sorry. Okay. So I said some correction with the previous explanation that before the settling time we call it as transient state. After the settling time we call it as steady state. So I have made a correction here. Please rectify this correction. So we'll take TS as a standard parameter to differentiate transient state and steady state. So what is transient state? Where there is unsettled oscillations. In steady state, where there is a oscillations which are settled, which stays within plus or minus 2%. So standard convention accepted is if if you subject any system with any input and if the oscillations are retained within plus or minus 2% of the final value, it is usually considered as steady state. Okay, but the ideal definition of steady state is there should be 0% oscillations, zero oscillations. But practical scenario, we are okay with just plus or minus 2% of oscillations. Okay, so many brains may be thinking why these oscillations are getting settled like this, why there is again no increase at all. Why we always get this type of response only. So we can get the answer for this eventually. So for time being, let us proceed with the settling time definition. So this is transient state, this is steady state. So let me erase this part of TS. So I hope it is clear for everyone. Any doubts with settling time? Because it's not the conventional rise time or peak time. It's quite different. Okay. If you have any queries, please you can stop me. I mean, if you have any conceptual doubt. So expression for TS is quite simpler than all other derivations. Again, we know C of t equal to this expression. And how to solve this for TS? So how to solve this equation for TS? Okay, of course, if you start writing something like C of TS equal to something something below 1.02, below 0.98. Okay, so this is a quite complicated derivation. This will become quite complicated derivation since we are associated with a numerical value. Okay, since this C of t is bounded with some value, the derivation of TS can be done only with a numerical solution. Numerical solution with some iterations and all simplification and all. So that is out of scope of our syllabus. So I won't be doing any. Why student is disturbing Okay, so since it is associated with a numerical value, to get the exact value of Ts, one has to go through numerical solution of this expression, and it is out of the scope of our discussion. So the following simplified derivation is accepted, where we can make the complicated derivation into a simpler one. So this is called approximation. So what approximation we are doing is just one step derivation for the t's. So that approximation is when e is to
Papa, kiwi fruit.
yeah, somebody is having any doubt? Anybody has any doubt? Okay, so what is that approximation is when settling time occurs, the value of e raised to minus zeta omega n into ts will be lesser than 0.02, will be lesser than 0.02. So how this approximation is made? Why only 0.02? If you have those queries, you can definitely try the numerical solution of this by keeping two bounds, upper bound as 1.02, lower bound as 0.92, and when you solve, you will get approximately this expression. Okay, I can also follow the reverse way to get the answer. Okay, so since it is out of scope, I have not dealt or derived much about this. So finally, you can simplify this expression to get Ts. So this will give us zeta omega and Ts equal to 4, or Ts equal to 4 by zeta omega n. So this is approximate value, which is generally accepted by all the designers. So this approximation is accepted for the exam also. So finally, we are done with rise time, peak time, and percentage peak overshoot, and settling time. And the next one is steady state error. We will do it in next class, steady state error. Okay, so please practice these derivations, and they may be asked in the exam. So that's fine. And before proceeding with the steady state error, I want to solve 2, 3 numericals. So should I directly display the solution of the answer? Is it okay for everyone? I'll write and I'll directly display and I will tell how to calculate and I will make you also to do it parallelly. Or is it okay if I record the video and just upload it the same way? Because time can be saved for me. In the regular class, we had a tutorial which is skipped in the online classes, because earlier we had thought that the offline classes would start from October 2nd. So with that intention, it was skipped, but again, the commencement of physical classes got postponed. So if I keep solving the numerical in the regular class, it consumes a lot of time. So instead, I thought I will just make a video of 2, 3 numerical and upload it in the same spreadsheet where you can watch it. And I will continue with the explanation of concepts and derivations in the regular class. So discuss and please inform it to Ganesh. What I prefer is to upload the videos in the same spreadsheet for the numericals, and in the continuous class I will continue with the concepts. Okay, so please, if possible, you try to adapt for this time, and once the